Bună ziua și bine v-am găsit la un nou ciclu al webinarului creat de Magic Engineering. Mă numesc Colin Gundiuc și în scurt timp voi începe prezentarea pentru noutățile legate de platforma 3D Experience și mai ales a rolurilor de stamping, die, face design sau, să zicem așa, creare de matrițe pe partea de tablă, atât progresive, clasice și în pași. În cadrul ciclului respectiv voi prezenta, sau cel puțin voi încerca să aduc noutățile ce au fost integrate în platforma 3D Experience, mai ales pe anul 2022 către cei de la Dassault System. Începând cu rolul de Stamping Die Designer, dar cum știți, începerea de conceptul a procesului de ștanțare, prima oară are loc aducerea piesei propriu-zise în platforma respectivă de 3D Experience sau deschiderea în CATIA. Pentru manufacturarea acestei piese, întotdeauna are loc o analiză propriu-zisă a piesei până a începe crearea matriței propriu-zise și prin această analiză are loc, în primul rând, verificarea suprafeței sau a suprafețelor piesei respective, corecția lor cu comenzi specifice din GSD sau alte workbench-uri din CATIA, cum ar fi, cum am specificat, GSD-ul sau comenzi de tip Healing Assistant, crearea unor suprafețe. Dacă ați lucrat vreodată cu CATIA, știți că importul de multe ori dintr-un alt sistem CAD, există posibilitatea să vă aducă procesele respective cu erori sau cu suprafețe chiar lipsă sau cu suprafețe distorsionate. Și atunci are loc crearea propriu-zisă a unor suprafețe noi. Prin această analiză propriu-zisă a profilului a formei suprafeței sau geometrică, este o zonă mai complexă, aș zice, din punct de vedere a procesului tehnologic și ea se împarte în mai multe tehnologii de analiză. Primul un ar fi, sau cel puțin cei de la Dassault așa zic, ar fi cel de draft analysis. Prin partea de draft analysis are loc identificarea poziției corecte de așezare a piesei sau a suprafeței pe suprafața de ștanțare, adică extragerea, să fie vizualizată extragerea propriu-zisă. Ea poate fi pusă ca și normală sau poate fi pusă sub un anumit unghi pentru procesul tehnologic care va urma în continuare în operațiile adiacente. Apoi, depth analysis sau analiza de adâncime. Orice suprafață care se va ambutisa are o anumită formă. Acea formă, în funcție de forma propriu-zisă a piesei, are adâncime. Ceea ce are loc prin această adâncime, formarea propriu-zisă sau curgerea formei a piesei de tablă, datorită elasticității, plasticității propriu-zise a materialului și calcularea fibrei acestei neutre cu ajutorul respectiv, cu softul. Calcularea apoi a zonelor de flange sau bordură și automat calcularea a spring back distance. Dacă ați lucrat în domeniul respectiv, cunoașteți acest noțiune de spring back distance, datorită și faptului că automat știți că orice piesă de tablă, datorită materialului din care este produsă piesa, are acest spring back, fiindcă datorită elasticității și plasticității are anumite momente de curgere care are loc și revenirea propriu-zisă a capetelor pe o anumită direcție, în care sunt utilizate anumite came pentru îndoirea piesei. Pentru formarea procesului tehnologic, la un moment dat, e nevoie și de o analiză de simulare sau de formare și acolo are loc și calcularea în platforma sau în cadrul CATIA din platforma 3D Experience a calculării acestui spring back distance pentru a vă ajuta și a calcula desfășurata completă și corectă a piesei și apoi dispunerea aceste desfășurate pe fiecare operație în parte pentru verificarea și crearea decupărilor, îndoirilor și deformărilor respective care vor reveni. Această calculare a compensării și a deformării are loc într-un pas adiacent, în pasul 3, prin formarea simulării respective. După calculul respectiv a simulării, are loc crearea desfășuratei și apoi, în funcție de forma piesei, calcularea sau crearea, aducerea de, să zic, de came specifice pentru îndoirea laturilor și verificarea în continuare a desfășuratei. Apoi are loc crearea pachetului de ansamblu, atât a părților active și a componentelor standardizate, cum ar fi plăci, bucșe, cilindre, coloane, came și altele. În video de mai jos este creat un video nou din partea de Dassault System care va prezenta primii pași pentru analiza și verificarea și până la crearea pachetului complet și a noutăților introduse în 2022 de către cei de la Dassault System și îl vom prezenta în continuare pentru a înțelege cât mai bine. Întrebările pe care le veți avea după vizionarea acestui film sunt dispus la sfârșitul videoului, le discutăm, dacă le aveți, dacă nu și apar pe parcurs, le puteți trimite mie pe e-mail sau colegilor noștri. Le voi despune la sfârșitul videoului și website-ul și pagina de LinkedIn în care putem contacta și discuta în legătură cu întrebările sau cererile pe care le aveți nevoie poate pentru achiziționarea platformei 3D Experience.
In 22 weeks, DIFACE Design, we have put the focus on the detailed design functionalities. We used to work a lot on the method planning to create a concept method plan from the final part, define the cutting tools, the draw operation and so on. And now we wanted to focus a little bit more on the detailed surface design. The use case we were targeted is the use case where you have to create quickly the extension surfaces of the part. So you quickly want to run a simulation and see the feasibility of the stamping. To do that, usually today the customers are using mesh surfaces because they are fast to create. The issue with that is that you need to redesign completely the surfaces with real surfaces in CATIA usually, so you can create the machining process. What we wanted to provide with this new function of DIFACE Design is the ability to quickly create directly detailed surfaces, so you can completely remove the step where you need to redesign your surfaces. This comes with several functions. One we call fillet connect, the other we call surface extension manager. And then we will also see some other functionalities inside DIFACE Design about the design change and knowledge integration. Let's start. So the first one is fillet connect. It's a simple functionalities which allows you to either fill a hole or extend the part surface. For example, here, if we take this big hole in the inside, it's something that is quite complex to fill because you need to connect several edges together, and then you need to do several patch inside. So this command allows you to automatically detect the lines to connect, the inner edges to connect. You can see 1, 2, 3, and then it creates the different patches with G1 tangency or G2 tangency. So it's really easy to actually fill a hole. You can also reuse it on the outside boundary if you want to connect, for example, two fillets together. Sometimes we have this configuration where the fillets are cut and we want to recreate the surface between the fillets. Again, you can use the automatic analysis. We will automatically find the right connection. And in some cases, for example here, you may want to modify a little bit the connection. So you can quickly click on the elements and start modifying the different connection. For example, here I'm clicking on number 3, then clicking on the new edge I want for this number 3 connection, and it is rerouted. We also have added in DIFACE Design 22X a new functionality to edit spline in 3D. So here, for example, it's a spline behind. You can edit spline and you can quickly drag the spline in 3D to modify it and shape the surface as you want. So here I'm just dragging one point a little bit more down. You can create new points, new control points, project them on a surface and so on. So it's really powerful. And then based on this spline, the new surface is created. So this is really nice to use and powerful tool, this fillet connect command. You can also use it manually. Let's take, for example, this example. Create a boundary. And in this case, I'm going to deactivate the automatic functionality, just to show you that it also can be done on any surfaces. For example, if the fillets are not real fillets, or if you have some difficulties to find the right pairs, you can manually define the pairs really quickly, just by clicking each pair one after the other, click apply, and again we create the small patches with the right quality. So this is Fillet Connect. The next function we're going to see is the Surface Extension Manager. This manager is really powerful, and it's based on what we call a boundary analysis. This is the feature that we can see. Boundary analysis, we just provide a boundary on the surface, and by clicking apply, it will compute several sections around the part. And for each section, based on geometrical criteria, the software can decide what kind of extension it should do to extend the part. The green, for example, is going to be what we call surface extension. The purple is going to be connect surfaces, and so on. Based on this analysis, we can start the Surface Extension Manager, select the boundary analysis as input, and click apply, and this manager, based on the minimum G2 and G1 length we provide, will automatically create the right feature based on the analysis. So you can, for example, see here some fillet connects. In green, you can see some surface extension. In gray, the connect surface. Of course, each surface is editable in the wizard. You can see here that I'm editing the fillet connect that we just saw. And you can also edit some sections type. For example, in this area here, which is defined by default as complex boundary, you can modify it and say surface extension, and then it will create a surface extension on this area. So this is really a powerful tool that will allow you to quickly compute a part extension all around a boundary. The software will choose for you the right solution, but you can still pretty easily redefine the different sections and modify the type manually. So those are really the core of the new functionalities of die-phase design in terms of detailed design. Then based on that, you can reuse what we already have presented in the previous webinar, for example, the wall surfaces, the connect surfaces, the wall surface extension manager, and so on. And quickly you can create a draw operation that you can send to the simulation. Here I'm just showing that you can modify the length if you want, and everything will be recomputed. Now, another aspect we are going to see about die-phase design is the design change. In die-phase design, if you remember, we had created a specific structure to manage the detailed design with some what we call links and detailed links. We're going to review all of that. 22x, it simplifies a little bit this process. For example, let's take this concept part here. Starting from this concept part, you will be able to create automatically a structure that will allow you to create the detailed design of each tool. For example, here I have my concept part which is done. I'm creating this structure generator command, selecting the process method plan feature, which represents my process, and selecting a target product. And this will create several representations inside the product, as well as links inside the detail parts, which are connected to the process part. So that means each time you modify the process part, it will also impact the detail part. We are really keeping the data continuity here. If we take a look at OP15, we can see this link to the OP15 step in my concept process. We can see inside that a tree is created, and in this tree a lot of features are retrieved automatically from the process, from the concept process. If I hide all the others representation here, this is what is done by default in OP15 part. And you have a new manager which allows you to quickly browse this structure with automatic ISO, and we will see it also automatic geometrical set activation. So you can have the same view as what you have in the wizard inside the detail part now, which enables you to browse the structure without knowing in depth what is inside the structure. It's really an easy view. Here, for example, we can quickly review the different cut tools and so on. It also creates what we call the result part. The result part, it is by default a copy of the concept part, so it contains the process with the concept geometry. And we will see in the next of the demo that this process result part will be automatically updated when we do the detail design in the several detail parts. So there is no more need for an user interaction to update my result part with the detail design. Here, for example, if I want to do the detail design of my punch contour, this is the concept punch contour that I got back from the concept part. Okay. This is my punch tool. You can of course manage or not automatic ISO. And if we take a look at the structure and what is happening when I select actually the elements in the wizard, you can see that for each tool you have a concept geometrical set, which contains the geometry from the process concept, the concept part, and you have a design geometrical set in which you should put your design of the detailed geometry. And when you select something in the wizard, it activates automatically the right set. So you don't need to ask yourself, where should I create my GSD features? For example, here, the set has been activated. I'm creating my sketch using the context bar. So you can see it is inside the design geometrical set. Then I'm just starting my design. So of course, this is not really a good design for a punch contour, but it's just to show you that it will update the result part. Creating some corners on my sketch. And you see that all of this is done inside the design geometrical set. Okay, now I'm done with the sketch. I'm just going to create a quick symmetry of all of this. And now let's say this is my detailed punch geometry. So I want to say to the system, hey, I have designed my geometry. Now I want to publish it as a detailed geometry. Using the detail part wizard, I just click on the tool, say affect tool detail geometry, and click on the geometry. And it will be automatically put into the detailed geometric set, which is a really important set because this set contains the geometry which will automatically be imported in the result part. So you see, using the detail part wizard, you don't need to understand the complex structure, you just need to play with the simplified structure. And then when you update the result part, you can see that the detailed geometry is automatically put inside the result part. So if we compare it, for example, to the concept part now, you can see in the concept part I had this design with the old punch contour, and now in this result part I have the new design. Without any user interaction, that's really powerful. This structure is also optimized for the design change. Let's say, for example, I have this method plan in the concept part, and I have several design change. I'm just going to do one in this video. Okay, you have a specific command inside this inside the typeface design application, which will allow you to quickly replace a part by one another and update the concept process. So let's say this is my updated part. You can see a difference in the shape, some difference in the holes positions also. And I think I'm going to use the 4 part. This one also has a small change on the flange on the left. This flange will not require a cam direction anymore, so we will also remove the cam from the process. So starting the new command, process part replace, and it guides the user, as you can see, with a wizard through the several steps needed to replace a part. First, you do the actual replace, you select the old geometry, and you replace it with the new geometry, just with simple clicks. You also have a preview in the 3D of what is the old, what is the new. The old is displayed in blue with transparency, and the new one is displayed with the actual color of the new surface. If you want, you can edit the nesting position. In this case, it's not really useful. Okay, it's almost the same part. Then step 2, we have to update the flange limit curve. So that's the line that are defining the flange in the part. You can put a specific geometrical tolerance if you want. Then you select the elements to update and you click update elements. And this is an update with automatic reconnection. So let's say you have an element to reconnect a B-rep that is not found again. You can see that 3 of those extracts have been automatically reconnected on the new geometry, because the geometry that we replace the first geometry by is a dead geometry, so there is no link, topological link. In this case, 3 extracts were automatically updated by this command because they were under the specified geometrical tolerance. And extract 4, we can see it is KO. So the command automatically displays the old geometry in blue. So you know what was the extract geometry before it was before the part was replaced. It gives you an overview of the old geometry. And then you can click edit elements and you can click on the new elements. This one, it was not automatically rerouted because the distance between the new geometry and the old geometry is over the specified tolerance in the command, which is one micron millimeter. So we click OK. You can also remove some elements from the method plan if in case a flange disappears and so on. Then the next step is to go into the process wizard and check that everything went fine. So here we are going to go into operation planning in OPS 35 because we want to check that the new flange geometry is still valid with our old process. It's not done in this video, but of course you need to check each geometry again with geometrical analysis, see if everything is fine, if the cut on the side is still correct. And here we have defined a cam direction for this hole, and we want to remove the cam and instead just use the press direction, because there is no more undercuts on this geometry. We still want to validate it. We want to check that the flange can actually be done. So we are using the review analysis window. Okay, here it shows it's a little bit vertical, but that's okay. We're going to ignore this verticality. And there is also, with the scan tool, we had also some filling tools inside, some pet tools that are on the other side. We are going to remove those tools from the process. Okay, because those tools, basically, they are not needed anymore since we do not have a cam. And now we have updated our process. We have checked that the tools are still valid with the geometrical analysis. And we are done with the actual design change for this part. Okay, so we can review operation by operation. We can see that the new geometry has been taken into account. And with those few steps, and the automatic relink geometrical tolerance, it's really easy to actually replace a part by another part. Next topic is about knowledge integration. With 22X, we have put into knowledge all the die phase design types. If we look at the die phase design catalog, you can see that all the types of the features of die phase design are inside. So this allows you to create a lot of rules inside knowledge. For example, to check that there is no cutting into OP15, check the number of operations, check the trim line length, check if the scraps elements are not too big. This allows you to introspect the data model of die phase design and create your own custom rules. For example, here, if in OP15, if I create a cut tool, then updating my rule, you can see that there is a warning. A cut tool is applied in OP15 and this is forbidden. Okay? This is my custom rule. So this integration into knowledge allows you to have really powerful checking rules that will allow you to have your custom validation of the die-phase design data model. This is really useful for customers, for example, that gets back a method plan from suppliers. Okay, and they want to check that it corresponds to their standards. They can implement their own custom rules and check that the rules are respected. Here, for example, I'm putting a process with 6 steps. Okay. This is still valid. If we check at my custom rule number of operation, I can see that I want the number of operation to be between 5 and 6. Okay, and if I add yet another step inside my process, and update the part to actually apply the rule, this time you can see that the rule is wrong, so we get a warning that says there is no press line allowing the current number of operations, which is 7. So this is really powerful. This next topic, and the last one for die-phase design, is about global unfold. You know, we have done a development with Simulia to compute the realistic unfold of a flange, and this one is about completely unflanging a surface. So you see I'm selecting a surface, and I'm also selecting some lines on this surface that I want to be projected on a plane. Clicking OK, and you can see that the unfold has been computed, the global unfold of the shape has been computed, and this one is done using geometric option. Because the global unfold, like the realistic trimline, you can do it with geometric computation to be fast, but not accurate, because the material behavior is not taken into account. And this command also allows you to select, so again, the surface and the elements to transfer, as well as the material mode. You can see geometric computation. I'm going to select material-based computation, and this will call Simulia on the background and compute an accurate global unfold of the shape. We can see it in black here. You can see the difference between the geometric and the realistic computation. So this is done with material behavior through a Simulia call directly into CATIA. Again, it's really simple to use. You can see that there is the inner hole that are projected, and it is really accurate based on simulation. Thank you for your attention. This ends the die-phase design webinar, and now we are going to switch to the virtual plural shape morphing webinar. Let's start with the video. Virtual plural shape morphing, it has been really a great year for this application. Basically what we have done, we have completely redesigned all the commands, and the application is almost brand new. It's still the same in the core, we still have the same functionalities, but all the commands has been redesigned with a new user experience, and we have also added a single command, a morphing wizard, which allows you to easily create a morphing of a shape with the right data model. The thing that we have seen with the previous version is that sometimes it was hard to use, and it was hard to understand what was the right data model, the right features to use in which cases, and how to actually combine those features together to have the best result. And with the wizard, we want to remove this complexity by providing only one single command which will put in place the right data model. Let's see how it works. So you can see the new toolbar here, and this is the wizard. Basically, you just select the element to morph, and the additional element that you want to morph, which means you want to apply the same morphing on those elements. Then you define the constraint, the symmetry planes, and for example the limit curve. So we can see a first evolution here. You can put as many limit curves as you want on the shape. I'm using a chaining edges here to define the limit curve. So those are the areas that are going to be frozen and not morphed on the part. You can see I'm putting several elements, and then for each limit curve you will be able to set several parameters like tangency, if you want to keep the tangency on the shape, like the area around the curve in which you want to do the transition area, in which you want to apply a transition morphing. between the actual morphing and the fixed area. So all of this is done inside the shape constraint area of the wizard. So here you can see the 4 limits curve. You can also have a preview of the side that is frozen. So you can see this one, for example, I want to freeze the inside and not the outside. The green is not frozen, the red is frozen. You can also specify what we call rigid holes. Rigid hole is a new functionality which allows you to keep the shape of a hole the same in regard of a given direction. So let's say, for example, this hole at the bottom, I'm going to punch it using the Z direction. I want that after the morphing, it keeps the same shape in the Z direction. Why? Because when you buy a tool in the workshop to cut the hole, in the end you're going to have the same tool. The tool is not going to be morphed. So even if the shape is deformed when you put it on the stamping press, the tool is the same. So you want to keep the same shape on the morphed surface. This allows you to define this kind of holes, rigid holes. Okay, so there are 2 rigid holes here, back in the main wizard. So we have selected the shape to deform, the constraint, and now we are defining on deformation. A new thing from this release is that you can actually have a link to a simulation, and this link is kept in the data model. It's not only a one-shot link. So here, for example, I am reusing my simulation results, and I want to compute the deformed shape outside of the simulation. On the background, everything is created. It's the law, the filter, the whole feature that we know for in virtual to shape morphing. You can still apply a filtering if you want to remove some vectors. The new filter that is available is this number of vectors to keep value. By default, before we used to keep only 30k vectors maximum. Now this is a completely open and free value, so you can keep as many vectors as you want. You can of course reduce if you want only to keep 10k, or you can put more if you want to keep more. And you can display actually the vectors that are removed, so you can control exactly what is happening. You have all the other filter fields that were existing before, and some display option. It's the same as before in this command. It's only the UI that has been reworked. You can also work on the tolerance. So as in the previous version of virtual dual shape morphing, you can set the tolerance, the vectors to ignore, the smoothing. What is new is that you can actually preview if the tolerance will be applied on all the vectors or not. So you will be able to see in green where the tolerance is respected, and in red where it is not respected. So that means the vector is ignored by the 0.1%. This is new. Before you couldn't have this view, where are my vectors ignored and what is my quality status. So here the smoothing is not activated because I have limit curve. This is still a limitation inside the software. And once I have done that, I just have to put my scale on the morphing I want. If I want to compensate, I'm putting -1. I have back also the tolerance directly in the main window. This is the same setting as in the tolerance window. And you click apply, and you have the morphing of all the shapes that you have selected. So in this case, we have a morphing of the surface, and we have also the projected curve to compensate morphing. You can see here the difference between the morphed surface and the previous result, the initial shape. And again, on the background, the right features has been created, the filter feature, the low feature, and the morphing feature, for example. So everything is done with one single command that is easy to use. That's for the wizard. Of course, you can still work with the previous command also, one by one. We will see it a little bit after this demo. Here I am modifying the simulation, so I am putting more pressure on this flange here, running the simulation anew. And what I would like to do after this simulation has been updated and computed, I want to update also my CATIA design from the new similar results. So this is not automatic because the similar result is not going to send a signal to the CATIA part that the displacement has been modified. You still need to have a manual interaction. This is done using this command, vector field link manager. So we can see it is linked to the simulation. And if we click apply, this is when the new vector field has been integrated into the morphing. So here you can see that we have a bigger gap between the two shapes. If you want to automate this behavior, this command is also available into a VBA API. So you can put macros on it and call this synchronized command automatically. Here I'm going to show you if you want to do command by command how it is working. So first you do the shape constraint, like before. You select the shape to deform, the symmetry plane and so on. Then you create a vector field, for example from a text file, which will create in 3D Experience a VPM document. So this document describes as a text document the vector field. And with this vector field command, I can create an actual CATIA vector field from this file. Then there are the standard command, transform, invert a vector field, which is a new command. It allows you to inverse the target and the source point. So it's not really a -1 transformation, it's really an inversion. Let's say your vector field is wrongly defined in the file and you want to invert it. This is the way to go. There is also a command that will allow you to merge two vector fields together, vector field assemble command, which is also new. And then you have the filter command, which has been redesigned. So you can find the same criteria as before, the number of vectors to keep, which is new. You can now choose the number you want to keep. And what we have done is that for each value, we have put a strong tooltip to explain what is actually doing. You have also the preview of, for example here, the distortion by color, and you can click on the arrow of the vectors to display the values vector by vector. Here is a distance color map, so you can see where is the biggest deformation. Then you create a law. Again, the UI has been redesigned, but it's the same functionality. We have added the new functionality to display quality status with the display mode. That's what we've seen before. So we can see in red the vectors that are ignored, for example. We can put some smoothing. And here you can see that the smoothing will actually put a higher tolerance on each node to have a smoother view. And we can also ignore more vectors. And then we have the morphing command. And which is new is that this morphing command works on a tessellation, on a mesh. You can see that this feature I want to deform is a mesh feature. It's a tessellation of the surface. And here you can see the result. So now virtual Tourelle shape morphic works also on mesh surfaces. Here I'm just showing that the result is also mesh surfaces, of course. If I'm pasting it as result, I will get a mesh. Now I'm going to show you that what works for the simulation when we updated the simulation with the link command. It also works with a document. So if I export my document as a text file, if I edit the text file, for example here I'm just going to put a factor 10 on some values. It has no sense, but it's just for the demonstration. Then I'm putting back the file into the database of the 3D experience. Again, this will not directly ask the part to update. There's no signal sent. This is a manual process, but you can automate it using CATVBA. And here, using the document reading command, it's synchronized, and we have a new result shape. You can see it's a little bit more wavy because I have modified values that are randomly modified, but it is a little bit more different than the previous one.
După cum ați observat și în partea video, a fost atât prezentată începutul, să zic, analizei și modificării conceptuale a procesului prin linkuri și la sfârșit simularea respectivă. Dacă aveți întrebări, la rândul său puteți să le puneți, pe care le cunosc, le voi explica acum, sau aveți posibilitatea să stați un pic, așa, să vizualizați și alte videouri, prezentări pe site-ul nostru Magic Engineering și inclusiv multe alte evenimente pe LinkedIn, pe pagina de LinkedIn și inclusiv și punerea de întrebări în cazul în care veți avea pe partea respectivă, dacă veți vizualiza acest video sau alte videouri, suntem la dispoziția dumneavoastră oricând și putem continua prin următoarele evenimente care vor fi prezentate de mine, Oleg Gundiuc, sau de colegul meu, Eugen Modrișan, în următoarele săptămâni. Din câte văd, întrebări nu sunt. Vă așteptăm în continuare la următoarele evenimente care vor apărea pe pagina de LinkedIn și video, veți avea acces la el într-un format video mai decent, poate cu explicații mult mai elocvente, pe site-ul nostru Magic Engineering. Vă doresc o zi bună și să ne vedem cu bine. La revedere!